Hello everyone, welcome to this presentation of this paper done by Victor van der Veen from Qualcomm and me, Ben Gras from Intel. This is a brief legal disclaimer on behalf of the legal department of Intel. I do not represent the opinions of Intel officially. Alright, so what is this presentation going to be about? This is going to be about, can we solve the problem of classical side channels? So classical side channels meaning microarchitectural effects that are observable as the result of secret dependent accesses that a victim is doing. Now these are of course well known as considered to be a software problem. Securely written software should not do secret dependent accesses. Nevertheless, wouldn't it be nice if we didn't have to worry about whether the software was secure or not? Maybe we want to use a known insecure implementation, or maybe we want some defense in depth. There have been cases where software that was thought to be constant time, didn't do any secret dependent accesses, by new microarchitectural insights, memjam is an example, became insecure. In that particular case, the granularity got improved from a cached line to a few words, and that made some current implementations insecure. So maybe you want defense in depth. So as an example, let's take a look at the code on this slide. This code is a point scalar multiplication, multiplying the point on an elliptic curve by a scalar. And the secret is the scalar. And as we see in this code, we only call the add function when the scalar bit is non-zero. And that is a secret dependent access, because if we can detect the fact that add point is being called, we know that the secret bit is 1. And if we don't detect it, we know that the secret bit is 0. So can we think of a way that we can execute this code without leaving any traces in the cache? Okay, so we're going to do that in the remainder of this presentation. First, we're going to propose a defense against this case. And spoiler alert, it's going to be a straw man immunity framework. So we're going to propose a defense that we can kind of anticipate is not a complete defense. It is a complete defense against cache attacks, but then we're going to look at some remaining exposure that's not in the cache, but in part number 2, DRAM. We're going to explain the drama side channel signal. And in the final part of this presentation, we're going to look at, can we use the drama side channel signal to exploit a known insecure victim in the presence of this cache attack immunity framework, to kind of quantify how powerful this side channel signal is in the case of all cache accesses being bypassed. Okay, so part number 1. Let's propose this cache attack immunity framework. Okay, so is there a way we can just forget about classical side channels? Meaning, is there a button we can push that will make classical side channels ineffective? So, as an idea, what if we simply force the victim in all secret processing code, in the insecure code, what if we force the victim to bypass all the caches? It can only make uncacheable code and data accesses while it's processing secrets. This means it will not leave a trace in the cache. Furthermore, we can also disable SMT, or we tell the operating system to inhibit scheduling different security domains on the same physical core at the same time, meaning other cache and microarchitectural buffers are also not shared. So you might think this is a perfectly secure situation. Classical side channels can now no longer be exploited. Very attractive. Okay, let's look at some exposure that remains in the form of the drama side channel signal, not in the cache, but in DRAM. So let's go over how DRAM works. DRAM is organized in rows. When the memory controller wants to read from a row in a particular bank, it sends a command to activate a particular row. And activating a row works like this. The contents of the row is copied to the row buffer, and once that has happened, the memory controller can send a read command, and then to read a particular set of columns from the row buffer, and then the DRAM will send those bytes over the bus in a reply like that. At some point, we do have to return the contents of the row buffer back to the row in DRAM, and this is done using the pre-charge command. Now, doing all of these things takes some time, and we cannot do anything in parallel because there's only one row buffer. So it's quite slow. So what we want to do is to spread out the workload, spread out DRAM accesses over as many different banks as possible so that all of these operations can happen in parallel, so that we can maximize the memory bandwidth and minimize latency. So, as an example, accessing rows in two different banks. In this example, we see bank 0 at the top and bank 1 at the bottom. We're accessing two different rows in parallel. That is fast because there's very little contention, very little shared resources. No serialization in the bank. But accessing two of the same rows in the same bank, as we see at the top here, that is going to be slow because then one row access has to wait for the other row access to happen. And that is, of course, the origin of this side channel that we're going to exploit. Because if I'm an attacker and I'm accessing one row over and over and over again, and then suddenly this latency goes up, then I can assume that someone in the same bank as my row is doing an access. So if that access is secret dependent, then I can start deducing secrets. And this schedule shows us an example of how come this access is slower if I'm accessing rows in the same bank. One has to wait for the other, causing this significant timing difference. So to show you a big picture of this phenomenon, here is a heat map where each pixel indicates an access latency. And this access latency is caused by accessing address number 1 on the x-axis and address number 2 on the y-axis in a loop. And most of the time, this latency is, well, medium. In exceptional cases, when the pixel is yellow, it's a very high latency. That's when the two addresses are in the same bank. So one row access has to wait for the other row. The two different rows in the same bank. And rarely there are two different rows, they're the same row in the same bank, and there the access is lower than usual because then there's no row switching necessary at all. Then the right row is always loaded in the row buffer and then it acts as a cache. So that's really the ideal case. Okay, can we use this bank conflict signal, this high latency signal, to observe victim behavior? So let's return to this victim code that does secret dependent behavior. So DRAM is of course a shared resource, just like CPU caches are. I'm going to try to exploit this fact by letting the attacker allocate memory that might be co-resident with the DRAM bank with the victim, and then see if we can use the attacker observed latency to deduce secrets. So in this proof of concept, we apply the cache attack immunization framework. So that means that the victim does only uncached accesses to the code and data pages in the victim code, in the secure code. This means that all of the accesses go straight to DRAM, and it means that we assume no cache attacks are possible. Then the attacker monitors a single address that we assume to be in the same DRAM bank as the victim, and the attacker finds this address by simply allocating a lot of memory and then trying to observe the latency accesses of uncached accesses of each cache line in that memory, and each time triggering the victim. And if the attacker observes a latency difference between a normal access and an access to the same piece of memory while the victim is executing, if latency goes up in the second case, then the attacker may assume, oh, perhaps this cache line is co-resident with wherever the victim happens to be. Okay, so let's see what the attacker then can see. The background shade here, the blue and the green, they show what the victim is doing at that moment. Is the victim executing the duplicate function, which happens unconditionally, or is the victim executing an add function, which happens conditionally? It only happens when the secret key bit is a 1. And the latency trace, the messy latency trace, is what the attacker can observe. Of course, the attacker doesn't really know the background shade, right, the ground truth, but the attacker can observe the latency. And if we know both, we know the ground truth and what the attacker sees. If we can see a correspondence between the latency that the attacker observes and the background shade, what the victim is doing, then we know we have likely a viable side channel. And as you can see in the second chart, where the latency signal is smoothed, there's a very strong correspondence. So can we exploit this fact? We exploit this fact by training a machine learning classifier, an SVM classifier, on the ground truth. So we let the victim execute, and we let the attacker collect traces. The attacker trains a classifier using the ground truth, and then on new traces uses the classifier to try and detect where the duplicate happens and where the add happens. And then, as you can see in the left chart, that classifier is very reliable. The red output is the red chart is the output of the classifier as the attacker processes the raw latency signal. So it correctly identifies the start of a blue region, start of a green region. It doesn't always work perfectly, and when it doesn't work perfectly, we use some heuristics and brute force to try and get to the real right key after all. And a histogram of how much brute force effort is required in different attempts can be seen in the right chart. And as you can see, usually less than 1 million attempts are necessary to find the real secret key that was being used. So this is a very practical side channel. So we conclude, this framework will probably work against cache attacks, but it'll probably not be a complete solution. We have to consider more shared resources like DRAM. The operating system may well be able to help by allowing memory to be allocated separately in banks, by making DRAM bank isolation possible. That was my presentation. Thank you for attention, everyone.